Making AI smarter with hormone simulation. While current AI, large language models, is stateless and purely mathematical, researchers are actively looking at ways to implement artificial neurochemistry. In humans, hormones don't just carry information, they act as global modulators. They change the sensitivity of entire neural circuits simultaneously. If we can replicate this, AI could move from being a reactive calculator to an agentic, self-regulating system. Here is how simulating hormones could fundamentally change AI architecture. 1. From static weights to dynamic modulation. Current AI models have fixed weights, parameters, after training. A neuron's response to an input is always the same. The hormone analog. Hormones like dopamine or norepinephrine don't change the physical structure of a brain, but they change how excitable neurons are. The AI application. Instead of just changing weights during training, backpropagation, we could implement a global gain control layer. An artificial hormone could temporarily increase the learning rate or sensitivity of certain layers across the entire network in response to specific environmental stimuli. 2. Solving the context window and attention problem. Transformers use attention mechanisms to decide what is important. However, this is computationally expensive and lacks a sense of urgency. The hormone analog, adrenaline, epinephrine, triggers a physiological state where the brain ignores peripheral tasks to focus on immediate threats. The AI application, an adrenaline signal, could act as a dynamic priority mask. When the system detects a high error rate or an urgent user command, it could trigger a mathematical narrowing of the attention mechanism, effectively forcing the model to drop all noise and dedicate all compute to a specific high-priority token sequence. 3. Long-term memory and value alignment. LLMs struggle with long-term mood or persistent values. They only know what is in their immediate context window. The hormone analog, oxytocin and cortisol, create long-lasting physiological states, bonding versus stress, that influence behavior for hours or days, far longer than a single electrical impulse. The AI application, we could implement slow-moving variables. While the transformer processes tokens in milliseconds, an artificial oxytocin layer would update a set of global parameters very slowly over time based on successful interactions. This would give the AI a personality or temperament that persists across different chat sessions. 4. Reinforcement learning, ARL, and drive. Currently, RL agents use a scalar reward signal, a single number. This is a very blunt instrument. The hormone analog. Human motivation is driven by complex chemical cocktails. Hunger, ghrelin, drives you to find food. Satiety, leptin, tells you to stop. The AI application. Instead of one reward number, an agent could have multiple internal drive states. An agent might have a curiosity hormone, driving exploration entropy, and a stability hormone, driving exploitation accuracy. The tension between these competing chemical signals would create much more complex, lifelike decision-making. The challenges. Why haven't we done this yet? 1. Mathematical complexity. Adding a layer of neurochemistry means adding more differential equations to an already massive computational load. It makes the model harder to train and slower to run, inference latency. 2. The gradient problem. Backpropagation relies on being able to calculate how much each weight contributed to an error. If you introduce hormonal fluctuations that change weights dynamically, it becomes incredibly difficult to track gradients through time. The vanishing gradient problem becomes even more chaotic. 3. Definition of chemicals. We don't yet have a mathematical definition for what digital dopamine actually looks like in terms of matrix multiplication. Is it a scalar multiplier, A bias shift? A change in the activation function, for example, moving from ReLU to sigmoid? Conclusion. Simulating hormones would move AI from logic-based processing toward homeostatic processing. The ultimate goal of artificial general intelligence, AGI, is likely not just a bigger model, but a model that possesses homeostasis, the ability to regulate its own internal state to survive and achieve goals in an unpredictable environment. Hormonal simulation is one of the most promising blueprints for achieving that regulation. Do you know that any private information you put into a cloud AI is used to train that AI? A private AI running on your own hardware is the best way to keep your private data private. I can help you set up a private AI on almost any PC or server. Contact me for a free consultation. If you get value from these blogs, please consider joining my Patreon as a member at the $2, $4, or $8 level. There are more than 400 previous blogs on my Patreon page. https://www.patreon.com/Steve Hovland.